Good morning. Welcome to Mission Control Houston. This is the International Space Station Flight Control Room, where there's a NASA team on duty around the clock, coordinating ground efforts worldwide to support operations on board the station and assist the astronauts and cosmonauts with their activities. For the Expedition 55 crew members this week, those activities have focused on scientific research, including some time spent on experiments that take advantage of the absence of gravity in this environment to learn more about fluid physics, and others for which the crew members themselves serve as the test subjects.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Dan Hewitt. It was another science-filled week aboard the orbiting laboratory. International Space Station crew members set up the Fluidics experiment. Fluidics is a fluid mechanics experiment with two main objectives: perform a slosh study to investigate how fluids move in microgravity during satellite maneuvers, and a wave turbulence study that isolates surface tension from gravity when looking at restoring forces. The study could also help us understand how oceans work here on Earth, including the phenomenon of rogue waves. Fluid mechanics wasn't the only thing on the crew's mind. They also spent some time studying, well, their minds. Expedition 55 flight engineers Scott Tingle and Norishige Kanai set up hardware for the neuromapping experiment, performing the test both strapped in and floating free. The neuromapping investigation uses brain scans to assess any changes in structure or function of the brain that occur after spending months on the space station. The investigation measures just how long it takes for the brain and body to recover from possible changes. Previous research and personal accounts from astronauts suggest movement control and cognition can be affected while in microgravity. This week's question comes from student Cooper Del Fosse of Sunrise Elementary in Sturgeon Bay, Wisconsin. He wants to know if you can see the Great Wall of China from space. Well, Cooper, although the Great Wall is frequently billed as the only man-made object visible from space, it generally is not, at least to the unaided eye. The Great Wall is pretty hard to see and hard to photograph because the material it's made out of is about the same color and texture as the area surrounding it. The shape, the age of the structure, the resolution of the camera, the condition of the atmosphere, all of these factors affect the ability to detect an object from low Earth orbit. However, you can see the wall in radar images taken from space. Station crew members take thousands of images of planet Earth during their time on board the space station. Head on over to eol.nasa.gov to check out the gateway to all astronaut photography. And keep sending in questions using the hashtag #SpaceToGround. We'll see you next week.
Next week, Commander Anton Shkaplerov, flight engineers Scott Tingle and Norishige Kanai will finalize their preparations to receive 3 new crewmates, and NASA TV and NASA.gov will provide live coverage of the major steps in this next crew transition. Soyuz Commander Oleg Artemyev and NASA astronauts Drew Feustel and Ricky Arnold will launch from the Baikonur Cosmodrome next Wednesday, March 21st. Our live coverage begins at 11:45 a.m. Central Time Wednesday morning, leading to a launch at 12:44 p.m. The Soyuz MS-08 will execute a 2-day rendezvous, so our docking coverage will begin next Friday afternoon, March 23rd, at 2 o'clock Houston time, and docking to the station's Poisk module will be at 2:41 p.m. We'll return at 4 p.m. Houston time for coverage of the hatch opening and the welcoming ceremony. And we'll have video coverage of the crew's pre-launch activities in Kazakhstan throughout the week next week. Ricky Arnold is about to begin his second space flight, which is also his first long-duration stay in space. He first flew on a Space Shuttle assembly mission which was in flight 9 years ago today. The Maryland native is a former classroom teacher who will take up the year of education on station responsibilities for the next 5 months, and they should only add to the interesting experiences he's already had in the classroom.
I graduated from college and was working at the United States Naval Academy in the oceanography department, and that's when I first considered becoming a teacher. My first teaching job was at the John Hanson Middle School in Waldorf, Maryland, and even though I was a science teacher, I actually taught 2 classes of social studies to go along with four classes of science. I coached high school basketball in Maryland at the Thomas Stone High School, as well as in Casablanca, Morocco, and in Bucharest, Romania. I played a guitar in rock and roll bands with fellow faculty members, administrators, and even some parents, both in Casablanca, Morocco, and in Bucharest, Romania. My first teaching job was in an open space science classroom with no running water. And I realized when I could get through my first year of teaching, I had really accomplished something.
In a few minutes, we'll have a look at 5 things you didn't know about astronaut Drew Feustel. One ongoing aspect of Ricky Arnold's mission on the International Space Station will be continuing the Year of Education on Station activities, which are designed to help teachers and students get the most out of learning about science, technology, engineering, and math. During this time, the various crew members have produced demonstration videos to help explain scientific concepts. In this new installment, Mark Vandehei takes on the topic of Newton's third law of motion.
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between 2 objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use 2 similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
Using data from experiments on the International Space Station, NASA is working with scientists around the world to build an open database of biological molecules. GeneLab is mapping the genes of organisms on the station and then making that information available to anyone so other scientists can develop and test out their own hypotheses.
With GeneLab, once the data is made available to us, it's posted on the world and it's available to anybody, anywhere. The research that's been conducted on ISS can be revisited, so those very valuable experiments that were flown in space, once this data is now open and anyone has access to it, other people can look at that spaceflight data and do useful things with it. And that's why that's what the openness means to me. He would like to see that data be useful for hypotheses and for experiments that have not yet been conceived. The researchers are being asked to go and do just that with GeneLab data, to come up with those new hypotheses and use that data to produce new results. We're struggling to try to make sure that we capture enough of the metadata because we have to answer questions that have not been thought of.
In addition to the biological research on the agenda, scientists are using the International Space Station to learn more about the physical sciences. For example, researchers behind a number of experiments on the science of combustion hope they can uncover ways to burn fuels so that the process produces less pollution.
The power of studying combustion on the ISS. Presented by Science at NASA. If you wanted to reduce the amount of pollution humans produce, where might you look? Here? Yep. Here? Sure. Here. Wait, what? That's exactly where scientists and researchers are looking, about 250 miles above Earth on the International Space Station. Here, astronauts are working on a series of experiments to learn more about combustion. Why combustion? Dennis Stocker, project scientist for the Advanced Combustion via Microgravity Experiments, or ACME, says, consider this. About 85% of the energy we use comes from combustion, the burning of some sort of fuel. About 70% of the electricity that we use at home and work comes from power plants that use combustion. The combustion of fuels powers the engines in many modes of transportation. Stocker continues, if we can learn more about the process, we might be able to find newer and less polluting ways to burn fuel. 3 series of combustion experiments taking place on the International Space Station's Combustion Integration Rack, or CIR, are looking at combustion in very different ways. The Flame Extinguishment Experiment, or FLEX, examined the burning of a single droplet of fuel in the microgravity confines of the ISS. The last of the droplet combustion experiments were conducted in September 2017. ACME began in November of 2017. ACME is composed of 6 major experiments, with each taking about 5 months to complete. These experiments will examine how various gases burn without gravity affecting the flames. The Solid Fuel Ignition and Extinction, or SOFI experiment, will explore the properties of burning solid matter. So why study combustion in microgravity? As Stocker explains, on the ISS you have conditions that you can't replicate on Earth. For example, consider a candle when it's burning. The flame flickers. Why? Hot gases from the flame rise, while cooler, denser air is pulled to the bottom of the flame. This flow occurs at high speeds, resulting in turbulence and instability. That instability makes it hard to study the properties of the flame. But on the ISS, there's no flicker, which allows us to make more precise and consistent measurements. If we have precise measurements, we get closer to learning how to burn more efficiently. More efficiency could lead to real cost savings for producing power. The research could also lead to reducing the production of soot and other pollutants. Combustion experiments conducted in space have contributed to practical applications on Earth, especially in the field of fire safety. A new type of fire extinguisher is just one example. And as Stocker notes, I think we're in for a few more surprises as a result of these microgravity experiments. That's because, not surprisingly, Stocker knew where to look for answers to reducing the amount of global pollution. He looked up. For more from the International Space Station, go to www.nasa.gov/station. If you're burning to learn more about other hot science topics, visit science.nasa.gov.
While there are many experiments at work inside the International Space Station's laboratories, there are cameras on the inside and outside of the station that are collecting imagery that can fascinate the human eye. For example, Here's some 4K video that was shot in August of 2016 as the station traveled nearly 1,000 miles, taking in views from the western coast of France all the way to the Balkan Peninsula. International Space Station crew members spend more than 2 years preparing for an individual mission. But for those of us who have a lot less time available to study, some of the crew members have been providing quick lessons on how things work on this vehicle. In this Speedy Time segment, astronaut Peggy Whitson pulls a rack out of the wall of the Destiny laboratory to show us how astronauts use the microgravity science glove box. It's a sealed environment that they use to perform science and technology experiments that involve potentially hazardous materials.
We wanted to talk to you about Microgravity Science's glove box. We do all kinds of experiments in here. I've grown tissue culture cells. I've looked at how air and fluid separate. I've grown superconductor crystals in here, and they got up to over 700 degrees Fahrenheit. So this environment was to protect us from what was happening inside the experiment. Now I'm growing cells, and they have to be grown in a sterile environment. So now I'm protecting the cells from me by having them inside this environment. So it's very flexible, and we can change out all the experiments by opening up this big door on the front. Then once we've got the experiment set up inside, you can access from the sides, or we have this little airlock down here that if you wanted to, you could access from here as well. It's kind of like a transformer. At the end of the day, when you're done working with it, you just push it back into the rack. There we go, and it fits right in very nicely within the rack volume. The other thing that goes along with this, or is attached to this, is a microscope. We have a fantastic microscope with capability to send the videos and pictures down to the ground. The ground's been looking at the structures that are forming differently here in zero gravity. That's why they're doing the research here, is to see what new they can discover. So very cool science, very cool piece of hardware. Microgravity Science's glove box.
The International Space Station is all about the science, such as experiments done inside the microgravity science glove box. It is also all about the supporting of future exploration and promoting international cooperation. And it is a key element in NASA's effort to promote the commercialization of spaceflight and space research as a